Hello everyone, it's Dr. London. Today we're going to look at some exponent rules. Just two rules, the product rule and the power rule for exponents. So let's just quickly recall the notation. Exponent notation is shorthand for repeated multiplication. For instance, let's say 5 to the third power would be 5 times 5 times 5, which is 125. So that's a much more compact way to write it. We don't always want to be writing out the number of expressions. It would just look funny to our eyes, and it would end up making the page look too confusing. So we have this notation to basically make it a little bit more efficient, a little bit more compact. So in the above example, five is the base. It's called the base, and 3 is the power or the exponent. So you'll hear either one of those used. And a lot of times we'll be using them for variables, so really this is kind of like an introduction to multiplying polynomials too. So you might have something like x to the third power. That again just represents x times x times x. So the two rules we have today, the first one we're going to look at is the product rule. And the product rule for exponents just says this. It says if you have the same base, let's say you have a to the m, and then you have another one with a matching base, a to the n, what do you do with the exponents in this case? Well, what you do, in all matter of fact, is you just add them. And that makes a lot of sense if you would just look at an example. Let's say you had, so the question is, when students see this expression a to the m times a to the n, a lot of times they'll mistakenly multiply m and n, but in this example, you add them. And the reason why, just imagine you had 3 to the second power times 3 to the fourth power. Well, you could expand that the way we did before we had the shorthand. We could say, okay, well, this one is 2 factors of 3, and the other one is 4 factors of 3. So I can just kind of put them in parentheses so we can separate them. And the parentheses really aren't doing anything. That's all you end up having is 6 factors. So 6 factors of 3, if you count them up. So that's why this becomes 3 to the 2 plus 4, which is 3 to the 6th power. So if you were writing it down and you wrote 3 to the 8th, it wouldn't really make sense. It's not fitting the definition of what we're using this exponent notation for. So let's practice simplifying a few of these with the product rule, and then we'll look at the power rule after that. So in this example, we want to simplify each expression using power rule or the product rule. So let's say we have 7 to the 8th times 7 to the 5th. Then you would just add the exponents. So this would be 7 to the 8 plus 5, which is 7 to the 13th. Now, you could put that in your calculator and get some huge number, but I just want to write everything in terms of simplified exponents. 7 to the 13 is going to be some gigantic number, and on the online homework it's set up the same way. B, let's have a look at negative 5 to the third times negative 5 to the fourth. Again, we're just have negative 5 raised to two different powers, and those are being multiplied together. So we just take the thing that's being raised to the powers, that's common, and we add those exponents. So 3 plus 4, and we get negative 5 to the 7th. Okay. What about if you have some expressions that have maybe some x's involved? So let's say we have negative 7 x to the 8th times 5x to the 6th. Well, what you do in this case is you just kind of group your regular numbers together and then group your x's together. So we'll have essentially 5 times negative 7, and then we'll have x to the 8th times x to the 6th. And since the x is the same base for each of those two, then we can use the power rule, or use the product rule, to add those exponents. So we're going to just do 5 times negative 7, that's negative 35, and for the other two we're going to add them, 8 plus 6, and so we end up with our answer of negative 35 x to the 14th power. Okay, and then for D, one thing you don't want to make a mistake on is if you have something like 4 to the 4th plus 4 to the 3rd, something like this. So essentially, the terms are added and not multiplied. So the product rule does not apply for this example. We might be able to do something with that a little bit later when we look at factoring, but not at the current moment. Okay, so let's go ahead and talk about the power rule. So the power rule for exponents, the other one we want to look at. So the power rule for exponents says if you have a to the m, and this is raised to another power n, then what you do in this instance is you actually multiply those two exponents. So this one is a to the m times n. And let's see if that makes sense. Let's say we had 3 squared, and we raise that to the 4th power. Well, what would that be? Well, that would be 3 squared multiplied out 4 times. And so you can count now that there's 8 factors of 3. And that's the same exact thing you would get as if you did 3 to the 2 times 4. So we are in fact multiplying those exponents rather than adding them, right? If you would add 2 and 4, you would get 6. So that's another positive reinforcement for why the power rule is true. So let's go ahead and try and do some examples where we work these out. So we're going to simplify using the power rule. So for A, let's say we have 3 to the 4th, and then this is squared. Well, this will just become 3 to the 4 times 2, or 3 to the 8th. And again, that's some number you can put in your calculator, but it's going to be relatively large, so I'm just going to leave it alone like that. B, on this one we have negative 3 to the 4th raised to the 4th. And the thing about that is really there's kind of two factors going on in here. You've got the -1 that's being raised to the 4th power, and then you also have your 3 to the 4th that's being raised to the 4th power. So if you take -1 and you raise it to any even power, that's always going to come out to +1. So this -1 to the 4th power, that just vanishes because you're just multiplying by 1. So we really just end up, in this case, with 3 to the 4 times 4 from the power rule, and that just comes out to 3 to the 16th. Again, I'm just going to leave it as is. No reason to put that in the calculator. B, let's go ahead and look at 2b cubed. So, so maybe I should just, and that's going to be part C. Maybe I should do a quick aside. So also related to the power rule, there's two other exponent rules I just want to mention additionally. So 2 additional rules that it might help you if I spell them out. And I don't know what their names are, but I always think about them separately. So, 1, if you have 2 things being raised to a power, a times b, and let's say that's raised to the nth power, then that's the same thing as a to the n times b to the n. Because really, you would just be writing a times b down n times, then shuffling all your a's to the left and your b's to the right, which is okay to do because of the commutative property, meaning it doesn't matter what order we multiply things in. And the second rule is it would work the same if we had a fraction and division were involved. So this could be simplified into a to the n over b to the n. And that's, again, easy to think about. You would just write down that fraction n times, and then you would just be multiplying the numerator so many times, and also the denominators. So let's continue with that previous example and see if maybe that makes some of these more clear. So let's say I have 2b to the 3rd power. So notice I'm using rule number 1. A is going to be behaving like 2, and b is going to be behaving like the actual b in the problem. So this would come out to 2 to the 3rd times b to the 3rd. And okay, maybe I'll simplify 2 to the 3rd because it's small. That would just be 8b to the 3rd. D, let's say we have 3/4 to the 3rd. Then this would be 3 to the 3rd over 4 to the 3rd, using that second example there. And 3 to the 3rd is going to be 27, and 4 to the 3rd is going to be 64. So that would simplify to 27 over 64. Let's do a couple examples that are similar but involve letters. So E, let's say we have 9x cubed times z to the 4th, and all of this is squared. Then really you're just using that same rule number 1 essentially twice, or 3 times. You're going to square the 9, then you're going to square the x to the 3rd, and then you're going to square the z to the 4th. And then from there, you're going to use the power rule because we need to multiply some exponents. 9 squared is 81, so I'll simplify that. X cubed squared, we multiply those exponents, so that becomes x to the 6th. And then z to the 4th squared, we multiply those exponents, so that becomes z to the 8th. For F, another similar one, maybe different letters. 4a to the 5th, b to the 4th squared. And again, we're just going to square each of the 3 parts. So we've got 4 squared, a to the 5th squared, and b to the 4th squared. So 4 squared is 16. Multiply your exponents for the remaining 2 parts. So 2 times 5 makes it a to the 10th, and 2 times 4 makes it b to the 8th. And so really that's all we're looking at in today's examples. So basically we wrote down 4 rules. We have these kind of 2 minor additional rules here. So maybe I'll box the 4 rules in. So these deal with when you have two things being raised, two different factors being raised to a power, either a times b to the n or a over b to the n. And we can recurse on that. So if we have three factors, we would, a times b times c to the n. That'd be a to the n times b to the n times c to the n. So we saw that in some examples. And then we had the power rule. So this is the second rule. And the first two rules both deal with how to essentially simplify a single an expression with the same base or matching bases. So you multiply when you have a to the m raised to the another power, and for the other one, if you have a to the m times a to the n, then we just add them. So those are the four rules that we looked at today. And going through the homework will help you get the hang of using these examples, and it's going to be very similar to the ones we just looked at here today. So anyhow, this is Dr. Lennon signing off for today.